Swayam Prabha. Digital India. Educated India.
Let us take another example. In the earlier example, the velocity component Vx depended on y and there was no y component, and so the normal strain rates were 0. Okay. They were 0 here, the diagonal elements represent the normal strain rates and they were 0. So, now let us take an example exactly which has the other component, namely the normal strain rate, but does not have shear strain rate and rotation. That is the use of that is object of this example. Okay. So, velocity field B is given by Axi minus Ayj. So, it is a 2 dimensional velocity field. You have both the x component and the y component. What does it physically represent? Represents flow in a corner, that is what is shown here in quadrant 1 and quadrant 2. So, let us take quadrant 1 for easy understanding, and A is a constant given as 0.3 second inverse and the coordinates are measured in meters. Now, A is given as 0.3 second inverse and the coordinates are measured in meters. Now, just like you marked two perpendicular lines in the earlier example, in this case we will mark a region. A square is marked in the fluid as shown at t equal to 0. So, this is a square marked at t equal to 0. Evaluate the new positions of the 4 corner points, something like what we did in the earlier case, after 1.35 seconds, after some time interval. Evaluate the rates of linear deformation in the x and y directions. Rates of linear deformation is nothing, is another way of saying rate of normal strain or normal strain rate in the x and y directions, and then compare area A dash B dash C dash, that will be the new area, A dash B dash C dash D dash will be the new area at 1.35 seconds, and then we have to compare with that area with the area A B C D at t equal to 0, whether it will change or not we will see that, okay. And then comment on the significance of this result. Okay. So, we have flow over a corner and then we are in this region, we are let us say marked with some red color dye this square region and we are tracking that. Okay. Now, how are we going to track that? Now, tracking a particular point is something similar to what we had done earlier. If you track a particle, it is equivalent to finding the path line of that particular particle. Okay. So, find position of particles. So, we have 4 particles A, B, C and then D. We will have to evaluate that position after some time interval, which is nothing but finding the path line. If you want to show the end the progress of these points, then we draw the path line, or if you want the only end point, then the end point of the path line will give you the final position. So, now we will find out the path line, so that at any time t we will know the position of A, B, C and D. Okay. So, let us find a general expression. So, we will have to recall what we discussed when we did examples on path lines and we discussed the theory for path lines. So, that is the velocity field. For finding out the path line, the physical principle what we used was that the velocity of the fluid, that is Eulerian description, which is equal to the velocity of the particle given by rate of its displacement, in the present case in the x direction. Okay. And this we have used when we discussed when we derived substantial derivative, when we discussed path line, same concept is being used here. The Eulerian velocity field is equal to velocity of the particle which happens to be at that particular location, which is given by the rate of change of its displacement, the present case x direction. And so, in the left hand side we evaluate the velocity field in terms of xp, and that is why I substituted x in terms of xp. So, now because our coordinates are x, I am going back to x, but that is a physical principle. Okay. So, dx by dt is equal to x. So, we have to just integrate this, do variable separation, integrate, and what are the initial conditions at time t equal to 0, x naught. What is x naught? Based on the particle which are going to take, let us say if we are going to take particle A, then x naught is 1. So, if we are going to take particle C, x naught is 2. So, x naught tells you the x coordinate of the particle at time t equal to 0, and you are going to find out x at any time t, and of course simple integration and rearrangement gives you x is equal to x naught e power a t. Okay. Now, let us do the same exercise for the y direction. We will equate the y component of velocity to the rate of change of y displacement of the particle, and here the y component of velocity is evaluated in terms of the y coordinate of the particle. Once again going back in terms of y, I get this differential equation relating y and time, dy by dt is equal to minus ay, variable separation, integration, and now the initial condition like in the earlier case t equal to 0, y equal to y naught. So, if you take particle d, the initial y coordinate is 1, if you take particle b, the initial y coordinate is 2. So, integration rearrangement gives you this equation relating the y coordinate of the particle as a function of time. So, at any time t you can calculate the x coordinate and the y coordinate, and in this particular case we are asked to calculate the coordinates. If you want to track this region as you progress, then you can substitute for different values of time and get the x and y coordinates. This example what we are asked to do is to find the coordinates at t equal to 1.35 seconds. So, in this table the first row shows the coordinates at time t equal to 0, second row shows the coordinates. How did I obtain? I just substituted t equal to 1.35 and x naught y naught depends on the particle. So, in fact these are the x naught y naught, and similarly for particle b, c and then d. So, substitute x naught y naught, substitute t equal to 1.35, then you will get the new x coordinate y coordinate of point A, similarly for b, c and then d. So, the second row gives the x and y coordinate of a, b, c, d after time interval of 1.35 seconds. Now, see the concept of path line was discussed some time back, and we have now used it and interpreting in a different way. What we have actually calculated is only path line, but now we are going to analyze in terms of what happens to this region and what is the implication of the velocity field on this particular region. Okay. Okay, so let us show the old and new position of the corner points. So, the this is a square region marked at time t equal to 0, and it has become a rectangle at t equal to 1.35 seconds. These are the coordinates of a dash, b dash, c dash and d dash, and it has become a rectangle. Okay. So, let us see how do we understand this. Okay. Now, the velocity field was given by ax I minus ay j. So, the rates of linear deformation, let us calculate them. The normal strain rates dou Vx by dou x is equal to a. In this, for this velocity field the x component depends on x. So, if you differentiate you get a non-zero value, unlike the earlier example. So, in general whenever the x component depends on the x coordinate, you will have a non-zero normal strain rate. Okay. And of course, the value is 0.3 second inverse, which means that there is elongation in the x direction. Now, let us evaluate the normal strain rate in the other direction, which is dou V y by dou y. So, differentiate the y component of velocity with respect to y, you get minus a, result is minus 0.3 second inverse, and which means that there is shortening in the y direction, okay. And that is what we have seen. If you see, compare B C and B dash C dash, there is elongation which is for line segment along x direction, and if you compare A B and then A dash B dash, there is a shortening in the line segment which was along the y direction, okay. So, for line segment along x direction there is elongation as shown by this value of 0.3 second inverse. Line segment along y direction there is decrease in that length and given by this minus 0.3 second inverse. Should keep in mind that, as we have discussed earlier, this tells about rate of elongation and also rate of change of length per unit length, okay. So, if you take a line at some time instant t, some time instant later, what is the increase in length divided by the original length, and this is instantaneous value, okay. Okay. What about rate of angular deformation, that is gamma dot x y, which is dou v y by dou x plus dou v x by dou y, is 0 because the V x does not depend on y, V y does not depend on x. If only if it is V x depends on y, like in the last case, then you will have a non-zero angular deformation, or in a, let us say in a 2 dimensional case, if V y depends on x, then again you will have a non-zero angular deformation. So, in this case there is no change in angle. When I say no change in angle, if you take 2 line segments perpendicular to each other, they remain as such. That is what you see here also. The angle BAD is 90 degrees, the angle B dash A dash D dash also 90 degrees, there is no change in angle at all, okay. That is why I said earlier example we had angular deformation and of course rotation. In this example angular deformation is 0, we will see rotation is also 0, but we have normal strain rates. So, the rate of rotation omega r at x y is same expression as earlier with the minus sign, of course it is 0, okay. Only if it depends, V y depends on x, V x depends on y, you will have, but they are not depending on x 1 y respectively, okay. Such a flow is called irrotational, where you do not have any rotation, such a flow is called irrotational, okay. And that is what you see in this animation. Now, for showing this animation, I calculate the coordinates at every instant of time. This A dash, B dash, C dash, D dash tells you the coordinates after some time t equal to 1.35 seconds. But now for this animation, I find out the path line equations, substitute t equal to 0, 0.1, 0.2, 0.3 whatever time interval, and then calculate the position and plot them, and the region covered by A B C D is shown as red, so that we see it as a region moving, okay. And as you see, it also represents the flow around the corner. If we have seen the streamlines where we had flow around the corner, and that is also represented by this region which you are tracking, okay. And we can see that the square becoming rectangle, how the square gradually becomes rectangle. This was only initial square, and then let us say a final rectangle at t equal to 1.35. Here you see how the square evolves gradually to the rectangle, and of course remember it is continuously deforms, that always should be kept in mind. We said fluid continuously deforms. So, as long as the flow and as long as you track, this will continue to deform. Of course, for the sake of simulation we have stopped and replaying it again, but otherwise continuously deforms, okay. So, in the earlier example no normal strain rates, only angular deformation, rotation were present. In this example normal strain rates are present, angular deformation and rotation are absent. Okay. Okay. This is a relatively simpler case compared to the earlier case. When you have angular deformation rotation, it becomes a little difficult to analyze in terms of the what you see and what we analyze. Remember, when we said in the earlier example, what we see is a summation of all the effects. Here, because no angular deformation and rotation, whatever you see is representing whatever we calculated in terms of normal strain rates. Earlier, it was representing both the combined effect of both the deformation and the rotation. Now, let us calculate the volumetric strain rate, and okay, let that be simulation be running. Okay. So, for the volumetric strain rate, we start with the velocity field, which is Axi minus Ayj. We have seen how to express volumetric strain rate, which is that fractional rate of change of volume. Okay. And we have seen that can be expressed in terms of del dot V. Okay. And del dot V has all these three terms, but in the present case we will have only the first two terms. Okay. So, let us evaluate them. Dou Vx by dou x is A, which is 0.3, dou Vy by dou y is minus A, which is minus 0.3, giving 0. What does it tell you? There is no change in volume. Rate of change of volume, of course normalized, fractional rate of change of volume is 0. The volume of the element does not change with respect to time. Okay. So, let us, in the present case it is not volume, it is area, because we are considering 2D. So, let us verify that numerically. The area of the initial square, both the sides are 1 unit or 1 meters. So, 1 meter squared. The final area should also be 1 meter square. Let us calculate that. What is the final area? A dash, B dash, C dash, D dash. If you consider points A dash and D dash, the length of the line A dash D dash, which is difference in the x coordinate of A dash D dash, which is 3 minus 3 by 2. Now, the height is the difference in the y coordinate of, let us say, A dash and B dash. So, it is 4 by 3 minus 2 by 3, and that is what is written here, 3 minus 3 by 2 into 4 by 3 minus 2 by 3, which gives us 1 meter squared. So, we have theoretically proved that the volume or area cannot change. Based on our calculation also, we have proved that the area does not change. So, no change in volume of fluid element. Why is it happening? The two rates of linear deformation are equal and opposite. The normal strain rate in the x direction is positive because length is increasing, and normal strain rate in the y direction is negative because the length is decreasing. They are equal and opposite, hence there is no change in the area. Okay. Whatever increase in area because of the increase in length along x direction is compensated by the decrease in area because of the decrease in length along the y direction. Okay. Of course, such a flow is incompressible, that is what we have seen. Okay. I would like to discuss another viewpoint. Remember, del dot V we expressed or discussed the significance in two different ways. The present way is that fractional rate of change of volume. Okay. Now, what is the earlier way? It was relating to a Eulerian viewpoint. The present viewpoint is Lagrangian, the earlier viewpoint is Eulerian, and remember these terms were derived as part of the continuity equation, where we took as control volume like this. Okay. Let us say if you take dou Vx by dou x, how did it come? We took the mass flow leaving to the right face, mass flow entering the left face, and then we took the difference, and so dou Vx by dou x represents, so let us say if you have rho there, it represents net mass flow leaving the x direction per unit volume. For the moment leave per unit volume. So, just represent something like net mass flow leaving in the x direction. Because there is no rho, it tells net rate at which volume leaves in the x direction. And what about dou Vy by dou y? That tells you net rate at which volume leaves in the y direction, of course per unit volume. Now, so if you look from a Eulerian viewpoint, if you take a small location, what happens is that because dou Vx by dou x is positive, which means that there is net flow leaving in the x direction, and then because dou V by dou y is negative, which means that there is net inflow in the y direction. They compensate each other, and hence the net rate of flow volume through all the control surfaces is equal to 0. Okay. So, that is two different viewpoints for del dot V. This example does not require the second viewpoint, but because we have discussed the two viewpoints of del dot V, and numerically we can see in this example that there is net outflow in one direction, the x direction, net inflow in the y direction, and hence the net flow, if you sum up all the through all the directions, is 0, other way of looking at it. Okay. Yeah, just to want to not a full example, but when we almost began the course, we introduced what a fluid particle is, and we defined a fluid particle as a small deforming volume, and then we took this example and showed that the fluid particle should represent whatever is happening to the flow field, and then we said along the flow field the particle elongates, becomes smaller, etc., in the other direction, etc. And we also showed this animation where we said the earlier title was demonstration of fluid particle. The same example now I say call it as a flow through a converging nozzle. Okay. And then we had simulations in two scales. One, when I just ran, we were tracking the fluid particle, and then we said should be very very small, and then we said for the same time interval it travels longer distance as it approaches as it travels along the length of the channel, because it is a converging channel, the velocity increases along the direction of flow. Then what we discussed was we zoomed this region, small this region, and then that is what we saw in the right animation, where we can clearly see that the fluid for the fluid element the length of the fluid element increases and then the height decreases. Okay. And then the statement which I made at that point of time was that the length increases because the velocity increases along the flow direction, and I said correspondingly there is a decrease in the height of the fluid element. Now they need not be accepted as such. Now we can by theory, based on our discussion, we can explain those statements. I will just repeat, earlier we have looked at this element, fluid element or fluid particle, and said that its length increases along the flow direction and height decreases along the flow direction. We explained saying that the length increases because the velocity increases along the flow direction. Correspondingly, I said the height decreases. Now we can physically reason out these two statements. That is what we will do in the next slide. Now what is the velocity field for a converging nozzle is given by this expression A into 1 plus x I minus a y j. But the way in which we should view is that the x velocity is a function of only x, the y velocity is a function of only y. That is how we should view for our purpose. For calculating rate of normal strain, shear strain, the x component of velocity depends on x. Then as we have calculated in the previous example, we have a non-zero value of dou Vx by dou x, and that is positive. Why? The x component increases along the x direction. That is also is line with the physics of the geometry. Because of the reduction in area, the x component should increase. Now what about the y direction? There is a it is minus a, and you have a minus 0.3 second inverse, and there is reduction in the height of the fluid element. So, because of this only, when we run the simulation, because of this only, this tells you that there is elongation in the x direction. Now, this clearly justifies our earlier statement that because the velocity increases along the x direction, there is elongation of the fluid element. Earlier we made as a qualitative statement, now we are quantitatively establishing that statement. If you look at the normal strain rate in the y direction, it is negative, and that is why you see a decrease in the height of the fluid element. Okay. Now, we made a statement that accordingly or correspondingly there is a decrease in the height of the fluid element. How do you explain that? Before that, like in the previous case, there is no angular deformation, there is no rotation, because Vx depends on x only, Vy depends on y only. If you calculate del dot V like in the earlier case, you get a value of 0. That is, this explains why accordingly or correspondingly, because it is incompressible flow, del dot V should be 0, and so when there is increase in length along x direction, it should be compensated by a decrease in length along the y direction. That is why we said increase in length along x direction because of increase in velocity, correspondingly there is a decrease in length along the y direction. Why that correspondingly? Because del dot V is incompressible, del dot V is 0 for incompressible flow. So, when one direction there is rate of increase in length, there is a decrease in rate of length in the other direction. Okay. So, we have kind of connected, we have seen this in the previous example in terms of concepts, just want to connect this example with the simulation which I have seen earlier, where we introduced the concept of particle. Okay. So, I think that brings us to the close of our this lecture, where we have discussed fluids, strain rate in fluids analogous to strain in solids. Okay. So, in terms of a journey to the Navier-Stokes, we were here where we have derived the differential form of linear momentum balance with the viscous stresses on the right hand side. We said we need to express that in terms of the velocity gradients. To understand velocity gradients, we took a diversion to solid mechanics, understood normal strain, shear strain, displacement gradient, rotation. We also understood how to decompose or split differential displacement in terms of deformation and rotation, and now we have analogously explained for the case of fluids, but everywhere we add rate. Okay. So, everywhere we add rate. So, normal strain rate, shear strain rate, and velocity gradient, and then the differential velocity is sum of deformation rate plus rotation rate. Superficially we say just addition of rate, but we discuss that based on the difference between the behavior of solids and fluids. And of course, now we will go back once again to solid mechanics to relate stress and then strain. We need to relate viscous stress and velocity gradients, and we said instead of velocity gradients we will relate only to the rate of deformation. But before doing that, we will go to solid mechanics once again to understand and relate stress and strain, so that when we come to fluid mechanics we can easily extend and relate the viscous stress and strain rate. Okay. Of course, this we will understand as we go along. Okay. To summarize, we started with a distinction between solids and fluids, okay, in terms of response to a tangential force, and we understood it's a deformation for solids, it's rate of deformation for fluids, and rate of deformation could be normal and shear strain rate. One is rate of change of length, other is rate of change of angle, and we also discussed that they are material derivatives of strain. Okay. We also discussed about rate of rotation, we discussed about volumetric strain rate, and the volumetric strain rate is represented by the divergence of velocity field, and so we understood two ways of or physical significance of the divergence of velocity in two different ways, and based on that we express the equation of continuity from the material particle viewpoint. We discussed the velocity gradient tensor analogous to the displacement gradient tensor for solids, and then we related the strain rate to the velocity gradient, and we also discussed the decomposition of fluid motion, which is expressing the velocity gradient tensor as sum of strain rate tensor and rotation rate tensor.